Let us now do the simulation of the push-pull converter. I have here in the folder, in the resources, I have a push-pull folder. Push-pull schematic is here, push-pull netlist, pushpull.cir, and the edt01.sub, which contains the subcircuit files. So let me double click on this. So you have the schematic. This is the complete schematic of the push-pull converter. You see the push-pull transformer here. The primary side is center tap. The secondary side is also center tap. There is this switch. I have used generic switches. This is Q1 and this is Q2, switch 2. I have placed here a 0 voltage source to sense the switch current. I have placed another 0 voltage source here to sense the Q2 switch current. Let me expand that. So here you see the push-pull circuit, and on the secondary side, which is center tap, the center tap is the reference node, and to the dot, from the dot end, you have a diode D1 ORing at this point with diode D2, which is coming from the non-dot end, and that is passed on to the inductor, capacitor, and R0 load. They are all connected to the center tap reference node. I have labeled the node here, output node O. I have labeled the gate drive node as G1 and G3 here. I'll tell you how I am getting that, and probably we can label a node here for the pole voltage VP. So you have the node VP here. Now EDT01 sub is included here, and all the subcircuits X, starting with X push, the push-pull transformer, the switches, they are all modeled in this edt01.sub. They have the subcircuit models which we can use. Then down here I have a PWM bridge which will generate 4 outputs. This can be used even for the full bridge. Therefore, I have made a generic PWM bridge block which will connect to ARM1 top switch, ARM1 bottom switch, 1T and 1B, ARM2 top switch, ARM2 bottom switch. These are the labels that I have given, and here you have the control voltage. I have given it as minus 0.5, comparing with a triangular waveform which is going from -1 to +1. So this will correspond to 25% switch duty cycle. So I am using G1 as one of the PWM signals, and for Q2 I am using G3 as the other PWM cycle, as the PWM signal. These two are mutually exclusive. So let me save the schematic. I have now opened the terminal, and let me make the netlist file pushpull.net from the pushpull.schematic file, and then simulate the pushpull.cir file in ngSpice. So on simulation, you will see the waveform. I have plotted the waveform, inductor current waveform IL, and the diode D1 waveform, because the diode waveform are very unique, and therefore, so it reaches steady state here around somewhere here. Let me zoom this, expand this portion. Let me see a few cycles here. You see. So you see that this is the inductor current waveform. So, and the diode D1 waveform, see, it follows the inductor current during this period when Q1 is on, and during the period when both are off, there is a freewheeling. Half of this freewheels through this diode and the other half will freewheel through diode D2. So the blue waveform is the diode D1 current waveform. If you look at the schematic, the output waveform is between O and R, and the pole waveform is between P and R. We can see the pole voltage waveform and the output voltage waveform. Going back to the ngSpice environment, I will plot voltage, the pole voltage waveform with respect to the reference node R, output voltage waveform with respect to the reference node R, and we'll see what we have. Let me expand that, and you see that you have the output voltage waveform and the red one is the pole voltage waveform. I will show few cycles here on the when it has reached steady state. Yes, so you see the output voltage blue waveform and the pole voltage waveform. The negative is due to the diode freewheeling, and this is n times Vi. So n Vi here, which is n, we have set it at 2. I have not shown you that one. Let me show you this. So this is push pull. When I double click, I have set NP primary turns as 10, secondary turns as 20, so turns ratio of 2. So you will have 10 into 2, 20 will be V pole voltage ideally, but there are diode drops which comes in during the simulation, so it will be less than 20. So that's what you are seeing here. The pole voltage waveform is hovering at 17.5 volts or so. So you have two diode drops coming to the picture. It's actually a diode drop and a VCSAT drop. So those two are the ones which are making up for this drop. You see also on the negative side, during freewheeling, the drop negative voltage is due to the diode drop. Let me show you two things. One is the EDT01 sub and the CIR files. So here if I double click on the pushpull.cir, you have this. It's a pushpull circuit. I have a dot options, relative tolerance and ABS tol I have set. So this is the dot trans statement. It is including pushpull.net. This is the control statements where I am setting the background as white and foreground as black, and running the plot command to visualize the inductor current and the diode D1 current. So this is the CIR file. Next I want to also show you the sub-circuit files. So in the sub-circuit file, so what do I have? I have the default diodes, of course, diode macro models, and I have the switch model which I have used. Then there is the electromagnetic transformer, the gyrator. These are called in turn by the push-pull transformer. This is the push-pull transformer that we are using, that sub-circuit which is calling the gyrators. So these models we have done using analog behavioral modeling. Of course, it is not within the scope of this course to cover analog behavioral modeling for simulation, but I am including this file. You can study it at leisure to understand that. And then down here I am including another analog behavioral model for PWM generation, which will generate the 4 PWMs for the 4 bridge switches. So this is simulating push-pull circuit. You are free to make changes and explore the circuit as much as possible. You can change the source, you can change the output, you can change the turns ratio, you can also change at the PWM the duty cycle, and check how it will work, how it will behave, and the voltages and the currents at various points in the push-pull circuit. Is it coming according to what we discussed and according to theory? And if it is not coming according to theory, where is the discrepancy, where is the non-ideality coming into the picture? These aspects you can study.